Supposedly it's Langlands, let's say. So what are we trying to do? So Langlands is about an equivalence of two categories at the end of the day. So there is a left-hand side and the right-hand side. So let's first talk about the left-hand side. So what is it? Okay, as the director said, we have a curve, smooth complete. X have a reductive group G, and we consider bond G. And again, it was written in the prerequisites that you guys have to know what it is. But I'll tell you what it is. All right, we consider bond G, and we consider the DG category of D modules and bond G. So first of all, okay, why DG category and what is it? Okay, so at the end of the day, or at the beginning of the day, we were interested in not the DG category, but the derived category of D modules. And at the end of the day, we might be interested in the same thing. I don't care about this higher categorical stuff. I want my derived category. All right, however, you might want it at the end, but in all the proofs, you'll have to go through DG categories for reasons that I'll explain in a second. So namely, just your derived category is your final output, but to manipulate it, you need to go through this more finer homotopy objects, the DG category. Okay, now what is it? So what is this gadget? So to say what this DG category is, I first have to say what this gadget is. And even before I say what this gadget is, I have to say what kind of gadget it is. So bond G is what we call a pre-stack. A pre-stack is just a functor out of the contravariant functor from affine schemes to groupoids. So affine schemes opposite to groupoids. So in this particular case, these are not even infinity groupoids, they're usual groupoids. Okay, so now if you have such a functor, the claim is that you can attach to it the DG category D modules on it. So what is it? Well, suppose we have a functor like this, call it Y. It's our pre-stack. So what is D modules on Y? So, well, roughly speaking, it is the following. So for every affine scheme mapping to your pre-stack, you want to assign, well, I'm saying what the objects are. Roughly, it's the following. For every affine scheme mapping to your Y, so for every S and a map from S to Y, by which I mean just an point here. So the datum of a map is an object in Y of S. For every one like this, you assign a D module, let me call it M sub S, inside the category of D modules on S. So I presume that we understand D modules and affine schemes. And whenever you have S prime mapping to S, so let me call this point little y. Let me call this F. Let me denote by Y prime the composition. So to any datum like this, you attach an isomorphism between what you had on S and what you have on S prime. So this F upper shriek is the functor of pullback on D modules. It's the only functor that we have on D modules. Okay, roughly this describes the objects. But, well, here the relevance of Sam's talk becomes important. Namely, well, it's all good if these are objects in the abelian category, but they are not. They are objects, well, in some kind of derived category. And so if you try to decipher what these words mean,
even in the abelian category, you want cocycle condition.
Yeah, there's, well, in the abelian category, you want some cocycle condition. You want to say that if S double prime maps to S prime, some two isomorphisms are the same. But if you're in this higher world, well, you have to specify all these isomorphisms up to what's called coherent homotopy, and this is an infinite kind of datum. And so this is exactly the kind of things that Sam was talking about. And so rigorously, what you do, you're saying that the category of d modules on y is what we call, well, the limit in the Sam that Sam was talking about of the following. So what do you mean by limit? So the semantics of speaking about limits is that you must have a functor from one category to another, and then you can take the limit of that functor. So so I'll write it, and then I'll say. So I'll write it symbolically like this, but let me decipher this notation. So I consider the following functor. I consider the category of affine schemes mapping to y, well denoted over y, opposite, and it has the functor to the category of DG categories. I call it DG cat, and it's the functor called, it's the following functor. So this functor has a forgetful functor to just affine schemes opposite. So here you have a functor, it's called the functor d mod. So to every affine scheme, you attach the category d mod of S. To every morphism, you attach the pullback. I'll stop here for a second, and I'll return to this point. You restrict this functor under this map. So a restriction of functors is an allowable composition. That's one of the things we're allowed to do. You can compose. Compose, you've got your functor, and then you take your limit in the sense that Sam was talking about. So limit is an allowable operation. OK, there is one catch here. Namely, I said that we have a functor called d mod from affine schemes opposite to DG categories. So I said that we have it. But what does it mean? So somebody had to construct this functor. So somebody, in addition to Jacob's orange book, there must be a green book somewhere where this green book must be constructing this functor. This green book doesn't yet exist, but hopefully it will exist in a couple of months. I don't know if it will be green or it depends on the publisher. Maybe it will be blue. If it's AMS, it's blue. Yeah. But again, so I'm saying that kind of the fact of the existence of this functor is not cheap. Something needs to be done to construct this. So anyway, all this was a detour. So again, so what are we doing? Gosh, so I explained what it means, how to construct the category of D modules on a pre-stack. So now let's...
So just a question about the last point. So is the problem, is it true that if all affine schemes were smooth, this problem wouldn't exist?
No, it would still exist, because you still have to specify these coherent homotopies. So if the affine schemes were smooth, you would be able to define the abelian category without any problems. But this abelian category is not enough because you do...
For quasi-coherent sheaves, does this problem exist?
For quasi-coherent sheaves, on what? On pre-stacks or on...
Just this
so
from affine schemes to DG categories. Is it easy to construct?
Easier.
But not immediate.
Not immediate. Something needs to be done. So, and again, you start with this functor, you construct this functor, you take the limit, and that is your category. Now let me return to the point why we want DG categories. Well, we need DG categories because...
So it claims that this functor for the moment doesn't really exist.
No, it exists. There is... No, it does exist. There are PDFs in which it's written. It's not yet a book, but it actually does exist.
This particular functor is, you're not using all of them. So this particular functor really does exist. This is just with pullback.
Okay, it does exist. Okay.
So it's easy to satisfy, to write down the universal property, but hard. So this is the correct.
Okay, I think we discussed this point enough. So there is... so one thing I want to explain, though, is that why I'm using the world of DG categories, not the world of triangulated categories that one might have been initially interested in. The problem is that, yes, there is the kind of category of triangulated categories. The problem is that it's a really badly behaved category. You could, in principle, in fact, easily write down the functor from schemes to the world of triangulated categories. You can take the limit there, but this limit will produce nonsense. So, I mean, it'll just produce not the answer you want. Okay, because kind of in some reasonable cases for your pre-stacks, or particularly for algebraic stacks, you have a very precise expectation of what you want the category to be. And if you write down this limit in the triangulated world, you'll just get wrong x's. So, and this is the reason why you have to work with DG categories. So all this nightmare of higher categories, it's introduced specifically to be able to take the limit and get the right thing in the answer. All right. So now I have to go back and tell you, well, who this y is. This y is Bunji.
But still, in this whole Bunji, there is an kind of alternative definition, kind of down-to-earth definition of the derived category.
Yeah, you can do. So what you can do, instead of like all schemes you can map, take some smooth cover, you'll go through some horrible pain of 15 pages. You can do it. But your definition will be very brittle. Like if you want to manipulate a little bit, you have to write another 15 pages. And you want to manipulate a little bit more, you have to write another 15 pages.
So you write a blue book.
Yeah, you write. So the thing that you write the blue book once.
Somebody else writes.
Yeah. Yes. Yeah. So you write it once, and then you're done for the rest of your life. So and not just for Bunji, you're done for all pre-stacks. So you just solve this problem once and for all, instead of doing it in each particular case. So that's why. Okay, now let me return and say who this y is. It's a pre-stack. So it's a again, it's a functor on the category of schemes, affine schemes. This functor is easy to write down. So affine scheme S goes to the following groupoid. Again, not infinity groupoid, it's an actual groupoid. So groupoid of principal G bundles on S times a curve. Objects are G bundles. Maps are isomorphisms, no homomorphisms. So that's the left-hand side of geometric Langlands. Any questions?
Yes. So
Yeah.
if we just consider the DG category as a simple, as a usual category.
What do you mean?
Not as an infinity category, but just
What do you mean? So there are objects,
objects and morphisms.
morphisms. Okay.
Can we still
So
define the limit?
so what do you do? So what did you? So a second. So what did you do with the two morphisms? Did you just So if two one morphisms were homotopic, do you identify them? Okay, say you do. Okay, so that's the sensible operation. No. I want to answer a question. It's sensible operation to do is the following: if you have a higher category, you can reduce it down. Basically, instead of what Sam did, instead of specifying identification of just any two one morphisms, say let me just declare them equal. And this is the procedure that starts from an infinity category. It produces an ordinary category. It's called the homotopic category. That homotopic category produces you the derived category, the triangulated category that you were initially interested in. So that's your final answer. The only thing you just can't, well, that'll be at the end, but not in the process. All right? Yes?
That doesn't sound like a good hope, but maybe you can actually compute the mod in some examples or not. I mean, it's like totally hopeless. You don't know what it looks like.
No, the thing is that it's actually very computable. So, yeah. So how do you actually compute? Okay, so that's the main thing about infinity categories. So it's written down by some machine. How do you actually make any computations? The thing is, it's actually easy. So, although it's very difficult to implement this by formulas, it's very easy to actually make concrete computations. So let me just give an example. So actually, maybe Nick will work out this example in his tutorial. So what the example I want to do is not Bunji, but BG, the classifying stack of an algebraic group. Where is Nick? So maybe you could do this. Just kind of explain how BG produces kind of the X that we want, just by some adjunction. So the thing is that kind of it has nice enough properties that you can have some adjoint functors with categories that you kind of are easily accessible, something like the category of vector spaces. And this allows you to actually do computations. So like basically the theory behind is very, very heavy, but once the theory is, once you accept it, the computations are easy. And so that's why the theory kind of works. All right. Okay. What did we do? The left-hand side. Now, the right-hand side. The right-hand side. Okay. So what's this right-hand side? Where was it? Damn it. Okay, let me just explain what I'm doing. So I'm not trying to give you an outline of like exactly how the proof will be constructed. I want to indicate why do we have some of the lectures, because some lectures look like very technical and boring stuff. Like, so what Sam was talking about, what Nick will talk about just in the next hour. And so you say, why on earth should I be sitting and listening to this interesting material? The thing is that what I'm trying to explain is why it's necessary. Like it might sound technical, but so unless you go into this technicality, you actually can't lift off the ground. Okay. So the left-hand side is this. So to a reductive group, there exists combinatorially, you can attach another group. It's called the Langlands dual. That's the easy part. You just invert your roots and co-roots, and you're done. G-check. So remember, you still have that curve that the director spoke about. And now you consider the following. Consider log cis with respect to G-check on your curve. So log cis, I'll explain what it is. It's the moduli stack of local systems on our curve with respect to G-check. So modulo modification that I'll explain in a couple of minutes, we'll be talking about the category of quasi-coherent sheaves and that. But now we have a whole new host of problems. The problem is that this guy is no longer what we call an ordinary stack, which you can probe by affine schemes. It's a derived stack and you have to probe it by what we call derived schemes. So, okay, I have to explain a little bit, well, to motivate the introduction of why this derived algebraic geometry appears. So what are schemes? I don't know what schemes are. I know what affine schemes are, spectra of rings, commutative rings. So derived algebraic geometry is constructed exactly the same way. You don't have to worry about like schemes. The only basic objects that you have are affine derived schemes. And those are spectra of derived rings. A derived rings is just commutative differential graded algebra that lives in non-positive degrees. CDGA with a tail in 0, -1, and so on. Okay, so why do we need these guys? So you can set up, instead of talking about prestacks, you can talk about derived prestacks. Just perceive your, well, instead of affine schemes, consider just these guys, the derived affine schemes. So the question is, why do you have to do that? So why could we not stay within the ordinary world of usual algebraic geometry? Well, here's the catch. Well, so what's a prestack? Again, it's a functor on the category of schemes, affine schemes. But suppose you can actually evaluate it not just on usual affine schemes, but you can evaluate it on derived affine schemes. Suppose it just makes sense. Well, in this case, you have your object in the world of derived algebraic geometry, or you could have evaluated the same guy on usual affine schemes, and you have the object in the ordinary algebraic geometry. So why should you prefer one over the other? Well, it just happens, it's experimental fact, that if your modular problem can be evaluated on the derived rings, that's what you have to do, because otherwise you'll produce a wrong category of quasi-coherent sheaves. So the thing is that if you have a derived ring A, and you can consider its zeroth cohomology, it will be the ordinary ring. You can consider A modules, well, and again, when I write this, I mean the DG category of A modules or modules with respect to its zeroth cohomology as a DG category. Now, if I were to consider the abelian categories, that would be the same. But the DG categories or the underlying derived category is drastically different. And experimentally, if you have a derived modular problem, i.e. the modular problem that can be evaluated in derived rings, you have to be doing the derived stuff, otherwise you'll just get a wrong answer. And this is what will happen if you were to consider log cis not in the derived world. So if you just want to have the right-hand side that will be eventually isomorphic to the left-hand side, you have to live in the world of derived algebraic geometry. So from now on, when I say, pardon me? Not always. Well, some of your pre-stacks are what's called classical, and Nick will explain this point. So some of the pre-stacks that can be evaluated on derived schemes, the entire information is already gotten from classical schemes, and so we call these pre-stacks classical. And again, this is so Nick will devote time to it in his tutorial. Okay, so now I haven't yet said what log_cis is, but let me run through the same story for what quasi-co is. So from now on, when I say pre-stack, I actually mean a derived pre-stack, i.e. a contravariant functor from derived defined schemes to groupoids. So again, let Y be a gadget like this. So what is quasi-co of Y? Well, it's exactly the same thing. It's the limit over now the category of affine derived schemes mapping to Y of, well, quasi-co of S. So it's exactly the same limit procedure, but not with respect, I'm applying it not to the functor d mod, but to the functor quasi-co. And that, well, spits out the category of quasi-coherent sheaves on your pre-stack. So, and again, it's very important here that, so these guys are derived because, so quasi-co on the derived scheme really depends on the derived structure. You cannot forget the lower cohomologies. So that's what quasi-co of log_cis will be once I set up what log_cis gcheck is. So I have to say who log_cis check is as a, well, a functor on derived defined schemes. So I have to say what is hom from a derived defined scheme S to log_cis gcheck. Well, what do you think it is? Seriously. So somebody who hasn't seen the definition but is confident enough, can you please make a suggestion?
Local systems of the product of.
Great. Okay, let's do it. So I like when there are bold people in the audience. All right. So you realize I'm leading you into a trap.
Yeah.
So you'll be slaughtered at the end, but we want to enjoy the show. All right. So Edward is saying, okay, we'll consider G-check local systems on S times X. Like this?
Well, in the derived sense.
Okay, first of all, it's already very wrong. Okay, you didn't want to do quite that because kind of you want them to be local systems only in the X direction, but quasi-coherent sheaves in the S direction. Okay, let's say we did this. But okay, but can you, what does it mean? So let's say S is a derived scheme. How do you make sense of such a gadget?
If X was a point, I guess I know.
Yeah, if S was a point, you can get away. The problem is that S now has this all this derived tail. Okay, let's forget, let's G be GLN, G-check GLN. So let's say just local system vector spaces, bundled with a connection. Yeah, so like if S was a point, you would say it's a bundle with
But maybe before the second, you can answer the question. But I mean, yes, your point was that if you can make sense of things in the derived setting, then you should do it.
Yeah.
How do you actually know that? Because I mean, obviously, if S was a usual scheme, not derived scheme, then it would be much easier to make sense.
Yeah.
Of this. And so, by looking at this, how do you know that you should actually also go to the derived?
Okay, it's an excellent question. That was it. So first of all, I look at it and I know that actually I can plug in the definition that I give. I can actually plug in derived schemes. There is a room for plugging in the derived scheme.
How do you know that? I mean,
How did I guess?
yes.
Say I guessed. I stared enough at it and then I.
For example, eventually, I mean, you mentioned the notion of classical things, so that's not for semi-simple groups, it will be classical.
Not on P1. On
Okay.
On P1, it will be derived. So basically, okay, I can start with the class. True. You're spoiling my story. Okay. Okay. Here's. Okay. Okay. Just a sec. Let me just answer him. However, you're totally right. However, in the process, we'll have also to do the Borel, and the Borel is always derived. Just yeah.
So you have a DG algebra, so you have a complex model. You have a model.
Are you trying to give this formula? Yeah, 1 second. I want to answer more Sasha's question. So, so it was about like exactly how did I know that I have to do it on the derived schemes? Because I first try on classical schemes, like for the torus. I get my definition. It just doesn't match the left-hand side. The cat I get is just not equivalent to what d bun g was. And then I see how different is it, and I see that it's different exactly by this annoying derived stuff. Then okay, then I say, okay, I have to go back and enlarge my definition so that to plug in derived schemes. Okay, now Sergey is trying to give the answer. So he says that, okay, E, we live over this. S is spec A. So what is E? It's a quasi-coherent sheaf on X.
It's a complex it's a model of this DG algebra.
Okay, it's a module for the DG algebra. Let's even X be affine for now. So you write such a thing, but then it's not an arbitrary map. It's not a map of O modules. It's a differential operator. So it satisfies the Leibniz rule. So what's Leibniz rule? F, gosh, I'm forgetting. What's the formula? What? DFE plus, great. So I don't remember the formula, and the problem is that it's a formula. And that's exactly the thing that Sam told us not to do. Because in the derived world, this F is an element of this ring, spec A times something. Not only will you have to write this formula, when you'll write del of F1 times F2, so it's no longer an equality, it'll be an homotopy. But then you'll have to say that if you write F1, F2, E, it'll be equal to something else in two different ways. You'll have to specify homotopy, then specify more homotopies, and there is no end to it. So so this is what.
Not only homotopies, but you're replacing your complex by.
Yeah, you have to express it by some resolution, and this is exactly what Sam meant, that you can't write formulas. So like this kind of thing, you can, but it's an infinite procedure. It's completely impracticable. So the thing is that you can no longer define connections by del. So you have to invent a different way of how how to make sense of vector bundle with the connection. And this is what Nick's talk will be about. So there's a procedure in, well, this derived algebraic geometry, how to say what the bundle and the connection is in allowable terms.
So if you use crystals instead of
Crystals is the answer. So
is it the only answer?
It is the only practicable answer.
So if you did try to do this, then you'd have to have a notion of a smooth affine.
No, nothing smooth will just, it's hopeless always. So you have to do crystals. All right. Great. Okay, so that's our left-hand side. So I haven't given the definition of log-sys. Nick will supply tools, and Dima will eventually give the definition. It's not very difficult, but it'll kind of, if the first time you see it, you said, ah. All right.
Is it right here to say that, like, on the left-hand side, the base object, it's like a simpler thing, but what lives over it is a more complicated.
That's exactly right. It's exactly right. So like the complexity of D modules is compensated by the simplicity of Bun-G. Here, quasi-co is simpler for the remaining minute. I'll make it more complicated right now. But the underlying category is more complicated. You have to use. So you could have asked, why did it not have to do the same with Bun-G? One with Bun-G, it was enough to stay with affine schemes. Because, well, Nick will explain that. I didn't say that. It's local systems on the product, local system in the direction of X. And we started saying this, and we got, well, we stumbled. We couldn't proceed because you have to write the formula. I don't know how to write a formula. So Nick will, as I said, Nick will explain the tools and Dima will give the definition. And I'm just indicating what will be happening in these talks. So like without some machinery, you just can't even formulate, well.
But there is also this idea that the model has some sort of diagonal. Maybe we can.
So that's roughly how the definition will proceed. Okay, but let's make it more complicated. Okay, so now we have the left-hand side, the right-hand side. We want to say this. The problem is that this is wrong, but it's not as wrong as like if you forgot about the right stuff. It's just slightly, it's a tiny bit wrong. So so the thing is that this, I don't know, there's a tech command that not kind of almost equality. It's like put a tiny bit cross here. Just it's a not almost. So it's almost, but it's like in mathematics, you want to prove something, and if it's almost true, you can't prove it because it's wrong.
You're not allowed to use equality.
Yeah. So it's actually wrong. So what I'll explain now is, so what you have to do, you have to tweak the left-hand side a little bit.
Which is now the right-hand side.
Which it doesn't matter. So I have to modify it by a category that, well, has this fancy notation, int co with nilp. You don't have to understand the symbols on log sys. All right. So what this is will be exactly the subject of Dima's third talk today and the first talk tomorrow. So he'll exactly explain how to perform this modification, but let me explain the need for it. So this need, and so this modification is kind of tiny, and that's the reason that people have overlooked it for some good 20 years. It's kind of, the difference is small enough that it's very, very difficult easy to overlook, and it has to do with these final aspects of homological algebra, but I'll try to indicate the main idea. So it has to do with the fact that this derived stack it's not smooth. So it has to do with the kind of singularities. So let's go back to our course on commutative algebra. So let's say A is even classical commutative ring, A. So let's consider the category of A mod. Well, when I write this, I always mean the derived category, but let's for now even consider the abelian category. So I denote it by a little heart. I don't know how to drive a... What's the technique of drawing a heart?
Like this.
What? All right. It's the abelian category and let's say A is Noetherian. So you know that this category is, well, and I consider all modules. This category is, well, kind of is governed by a much smaller category of finitely generated modules. So inside there is
Why do you put a heart?
I want to talk about the abelian category for a minute.
Oh, so heart means
Heart means the abelian category, the heart of the T structure. So inside there are finitely generated modules, and so this entire category can be recovered from this one by a formal procedure. It's called the int completion. So basically any module is a filtered, well, a union of finitely generated submodules. And kind of any kind of operation that you write on all modules can be expressed through an operation on finite. Pardon me, A is Noetherian here. All right, but now, so that's the usual thing in the abelian world. But now let's go to the derived world. And again, this category is what's called well, it's a big category. And inside, I want to find a category that plays a similar role, that I can get all A modules by a formal procedure from, well, this kind of some notion of finitely generated ones. So here is your obvious guess. Well, I'll take, well, you know what? I'll write to call it quasi-co of S. S is spec A, just easier for me notationally. So the category that I initially attempt to write is what I call co of S. In terms of A modules, these are complexes that have cohomologies infinitely many degrees, and the cohomologies are finitely generated. So the cohomologies are these guys.
So quasi-coh means DG category, not
Yeah.
derived category.
Here it doesn't matter. It's like it's a question. DG versus derived has to do when you have to perform operations on categories. When you stay within a given category, that doesn't matter. We're talking about homological algebra within a given category. All right. So I'm considering co again, complexes with cohomologies infinitely many degrees, and each cohomology finitely generated. So you can ask the following procedure: can I recover all of these from these by the same kind of completion? So basically, I want to, well, add all formal direct sums and take all possible cones, and can I get this from this? Yes or no? So no. What's the?
You can, but you get too much.
Well, you know the answer. But Emmanuel, why did you say no? No, 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 no. You can't go back.
Just guess. So
No.
But can you get it for something else? Can you? So, okay, the answer is no in general. But is there something like this from which you can get it? To take what? Yeah. So it's correct that int of this is not that, and it's int of this will be more than this. But do you have a guess? Int of what will be exactly this? Who said that? Perfect. Indeed. And so indeed. So inside quasi-co of S, there are two guys. There is co of S and what I'll call perf of S. So perf of S is what? These are, again, complexes, but the condition is different. I want these complexes to be, well, quasi-isomorphic to finite complexes of projectives. So it's a stronger condition than just having finitely many cohomologies and each cohomology finitely generated. So I want the complex to be actually modeled by a finite complex of projectives. And so this sits, of course, inside, and you can actually say who it is among these. These are guys of what's called finite Tor dimension. And so just a different, smaller subcategory. And now it is true that if you take the int completion of perf, this will be quasi-co. But you can still formally take the int completion of co, and this is what I call, surprise, surprise, int co. It's just a different guy. So now the two categories are related by a pair of functors. Because perf sits inside int co, well, the formation of int completion is functorial. There is a functor in this direction, and this functor has the right adjoint basically because, well, kind of every coherent is in particular quasi-coherent. I can put them back in and indextend. So this coulter is called Xi of S, and this coulter is called Phi of S. And so this functor is fully faithful, and this is kind of quotienting. And so this is exactly what this modification has to do with. So initially you thought you might want this category, but it's too small. And if you take S will be this log cis, and this will be too large. What you have to do, you have to find something in between. And this is what... Well, I haven't said what the T structure is, but there is T structure, and indeed, so T structure is what's called non-separated. There are objects, all of whose cohomologies are 0 in here, and yet the objects are not 0. If you kill those, you get quasi-co back. So this symbol nilp is some notation for a category that will be intermediate between those two. And that's how it comes about.
Quick question, sorry.
Yeah.
Distinction between perfect complexes and coherent complexes only comes up for singular S.
So I forgot to mention that. There are cases when the two are the same, and it's the case when S is smooth. F is smooth, anything which is, anything has a finite order dimension. So the finite order dimension condition is vacuous, and therefore it's an equality. So there's no distinction for smooth things. And it's kind of the measure of how non-smooth S is. So in fact, what people do nowadays, independently of any kind of Langlands stuff, it's a full subcategory. Take the quotient, it's called the category of singularities of S, and it's extensively studied by many people for various reasons. Okay, so this will be the subject of Demos talks of singular support. Okay, so now I have gone for 45 minutes and I've covered a third of what I wanted to do. God. Yes.
I'm just curious, so when you take this Q code, it's already incomplete, and it has co in it. So in some sense, if you inside of there wanted an incomplete co, you wouldn't get anything different.
Say again?
If you were to try it, so this Q code is already incomplete, right?
Q code is incomplete, yes.
Something you could call co. In some sense, if you want to take incompletion of co in there, it's already Q code.
No. No. So incompletion is the abstract procedure. Incompletion is not incompletion within something. You just formally add direct sums. You add them formally, and you don't impose any relations other than relations that come from co. I could have added relations that come from quasi-co. Okay, incompletion, okay? It's a separate thing. It maps to quasi-co. And as you're saying, it maps surjectively because of the reasons you're saying, but it does not map injectively because there are more relations in this int co. You kind of you're adding your direct sums freely.
So you think there's more relations in Q code?
Okay, I think I've said enough. So section 1 of the int co paper, you'll know all you want to know. Okay, in the remaining 15 minutes, let me try to roughly say, okay, so this is kind of the statement. So let me now indicate what will be happening after we're done with the statement. We'll actually want to proceed to the proof. So let me just give some indication of, how we'll be doing it. And we'll start with the geometric side, the automorphic side. G is reductive here. So, kind of to motivate what we'll be doing, so we have this D mod of bond G, and it's complicated. So, again, we want to make it equivalent to something else, but both sides are very complicated. So what we want to do, the idea of the whole approach, is to map them, or rather embed them into something much simpler. So if you're familiar with the basic concepts of number theory, so global fields are much more difficult than local fields. So kind of global fields, they carry what's called the arithmetic information. And the global field is kind of encoded by this smooth and complete curve, as the director said. So you want to embed this category something local. And this local, what do I mean by local? It's something that kind of factors according to the points of your curve. I want to say the product of tensor product or points of the curve of some simpler categories. And these simpler categories is what I'll call the Whittaker categories of my group G. Okay, so there are many problems here. First of all, you guys know what tensor product is, right? Hopefully. But you know what tensor product is of, say, vector spaces. Here we're taking the tensor product of categories. So this notion may be less familiar, and again, this is what Nick will explain. So the world of DG categories allows for tensor products. Well, secondly, it's a tensor product over an infinite set. Take an infinite product over all points of the curve. Again, this is familiar in number theory when we talked about, well, if you know about automorphic representations, there you take what's called a restricted product. It'll be kind of like this here. And so the formulas for this kind of gadgets will be Sam's talk on factorization. So Sam, in his first talk on day 3, he will introduce the notion of factorization category, and it's exactly the structure. It's basically an assignment for every point of a curve of a certain category, and it's a structure that allows you to make sense of this expression. And the kind of technically, if C is a factorization category, we'll call C sub Ran. Ran is a guy. It's not a mathematical term, it's a last name. And so it'll be kind of this restricted tensor product. So Sam will explain the technique of forming such things. And the whole idea is that kind of each of these categories depends, well, doesn't feel the global curve. It only depends on one point. And so we'll be able to embed almost fully faithfully our category into such a simpler thing, and well, this will allow us to analyze it. All right. Okay. Let me say a few words what this category will actually be. Well, I just indicate kind of the spirit of things. So for each point x, the category will look as follows. Again, well, I'll say some words. You shouldn't be scared, although these words are listed as prerequisites, but kind of you still have two days to kind of study up on this. So what is this Whittaker category? It's the following. So you consider, well, kind of more scary objects. You consider the affine Grassmannian for the group G at the point x. This is the quotient of what we call the loop group by the group of arcs. You consider the category of D modules on this horrible space, and it's again, it's another kind of pre-stack. It's an ind scheme, but you define D modules on it as a pre-stack by the procedure we defined, and then you impose an equivariance condition with respect to the group of loops into n against a character. See, there are many things that need to be introduced here. So what is this character? What does it mean to be equivariant? And so on. So, and this will be done in Dario's talks on day 2 and day 4. So this is the Whittaker category. Well, the definition looks complicated enough, but at the end of the day, it will be very useful. So it will allow us to embed our category into something much simpler. So this is what will be happening on the geometric side of Langlands. So if you have an algebraic variety, Kx is the local field of your point. So you can take the loop group at that point.
What is M?
The unipotent, maximum unipotent of G, okay? So these guys are all scary. So these are like groups of infinite type. So some care is needed when defining these categories. So we'll do it slowly of the course of several days.
Do we have this at the level of functions?
Yeah, so we have it. So the reason we're doing this, there's a very strong motivation that comes from number theory, because so this procedure on the geometric side is mimicking what's happening at the level of, well, in number theory. Again, this is explained in the notes, and it'll be explained even.
Function is very far from an embedding, right?
And it's not an embedding on D modules either. You have to add something, which I'm currently not explaining for the lack of time. It's actually in the notes. If you read the notes of the talk for this talk, you'll see that. So the map that is explaining the notes is not an embedding. You have to complement it by something to make it an embedding, and you can do the same for functions. And for GLN, it will be an embedding for functions as well.
That's more what I meant.
you mean GLN versus non-GLN?
Yes.
Yeah, so again, so this is addressed in the notes. All right, so
Actually, notes to what lecture?
this lecture. So every lecture has lecture notes on the web, and it's people are highly advised to read these lectures after or even before. So before is better because you. Pardon? Well, partly. Yeah, tutorials. Yeah, tutorials don't get lecture notes. All right, so this is what's happening on the geometric side. And again, so thank you, Sergey, for the clarification. So indeed, this is modeling what's happening in number theory. So now I'll mention what's happening on the spectral side, i.e. Galois side of Langlands correspondence. So there we have this, let me just write quasi-co without this modification. So you also want to, well, by the same logic, you want to map it to something much simpler. And what would this simpler be? Well, whereas this has a very close analog in number theory, what's happening on the left, well, on the spectral side, spectral refers to log-cis, does not have such a close analog in number theory. So that was a kind of a guess that people had to make. But it does embed into something local, and this something local is actually something very familiar. So we consider just the category of representations of algebraic group G check, and you put it at every point of the curve. Well, turns out that this category has a natural factorization structure, and you can make sense of this restricted product. We call it rep G check run. And so what will be explained in Nick's talk on day 4, it's called the local to global principle, is that we will be able to embed this category again into this local object. And then,
Also embedding some peculiar sense?
no, this will be in embedding as is, but of quasi-co. But it will not be embedding of that int-co stuff. And so exactly what you're using by passage from int-co to quasi-co, it's exactly responsible for this function not being fully faithful. So if you didn't know about this modification that I mentioned, you would run into contradiction mathematics because you would expect this to be fully faithful as well. So what is killed here is exactly corresponds to the difference between int-co and quasi-co.
Is it possible to say what is d-module analog of quasi-co?
Pardon me?
Is it possible to define some kind of d-modules which is kind of
Which is not in quasi-co.
No, which is equivalent to quasi-co?
Yeah. So let me first say who is not. So under this equivalence, let me say which emphatically something that emphatically does not go to quasi-co. This is the constant d-module. Inside here, it is possible to single out subcategory that corresponds to quasi-co. That's called the tempered guys. This
Both a quasi-category and a quotient category.
We're getting a little bit more technical, so let me just. All right. So this will be explained in Nick's talk, and then on day 5, what we'll do, we'll construct a local equivalence between these Whittaker categories all the way to these representation categories. So we'll match up the larger local categories. Well, again, we'll be able to match them because they're much simpler. And then, not that we have a proof at that point, but at least we have a much better formulation. Because you see, if these, let's pretend that they both sit fully faithfully, if you matched up the bigger categories, it's now the yes or no question of matching these two. All you want that their essential images coincide. So even when I stated the Langlands conjecture, well, I didn't say any properties that I wanted it to satisfy. Now at least I have the property. I want them not to be just abstractly equivalent. I want them to be equal as subcategories of this and this respectively under this local equivalence. And this is how the proof will proceed. We'll identify the local categories, and then we'll show that, well, by basic exhibiting generators and relations, that the essential images actually coincide.
So this is where opers.
This is when opers appear. So kind of the fact that the images coincide will be the content of day 6. So all up to day 5, we'll be setting up this picture. On day 6, well, basically what will happen is that we'll hit this diagram, by another diagram from below. There'll be another good diagram. It has to do with Kac-Moody algebras, and by hitting it from below, we'll match up the essential images. So that's the kind of, that's the...
But both are not embedding, right?
Well, we'll correct them to make them embeddings. We'll enlarge this to something, and then we'll enlarge this to something to make them embeddings, and then... So, pardon me? Modulo technical, a lot of technical stuff.
So could you describe the image?
Pardon me?
Describe the image.
No. Not in any explicit way. So...
So that's correctly that the only incompleteness in the proof is what refers to day 6. That's right.
No, the actual incompleteness is what something that has to do with day 5 is like. Well, you'll see. You'll see exactly what's happening. All right. Yes.
Can you obtain some information for the abelian part of this?
Abelian?
Like as it was at the beginning, you start.
Oh, the abelian categories. Yes. Very good question. None at all. Because so both categories have a T structure. You can, but this functor is as inexact as it can be. So it maps objects from the abelian category to objects that. So you can start with the constant sheaf here, which lives in the heart of the T structure, to an object here, which has 0 cohomologies everywhere.
Sometimes you're wrong, because for very low change between objects on both sides, which go objects in the abelian category on both sides, which go to abelian objects in the
Yeah, there are parts which match up even with the T structure, but the entire categories, the T structures are wildly incompatible. As I'm saying, something in the heart goes to something which is cohomologically 0.
So is this finally a sort of causal?
Pardon?
Yes.
Pardon? Say again?
My question is whether this is finally a sort of causal.
Maybe. So Ivan said yes. Let him answer, because I don't see any causal analogy here.
Who said yes?
Ivan, please.
At least for the forest.
It's not causal.
So there are these nice abelian parts that match. Do they, in some sense, generate the whole category as some kind of homotopy category of this?
Good question, not that I know of. It's exactly the kind of questions that haven't been explored yet.
Can you repeat the question?
So, even saying, so as you said, there are parts that are in the heart of the T structure that match up. Even saying, are these parts large enough that they generate the entire category? Well, they don't generate the entire category. Maybe they generate up to something more easily understandable, but I don't know.
So classically, this is easy to analyze this question.
Again, so this is something that hasn't been explored, at least to my knowledge.
Then can I say a couple of thoughts on what generality it is at least assumed to be proved? GL2, GLN, general?
Well, for GL2, there is direct path. So if he, or Sam, when he finally writes what I thought would be in his thesis, we'll have the proof for GL2. GLN will involve much of the same stuff with a lot of more technical work, because there's no real kind of hardcore abstraction. For other groups, there is hardcore abstraction that has to do with this functor. We don't know much about this functor for groups other than GLN.
Okay, so means this you cannot make fully faithful.
We conjecture it's fully faithful. Again, you can read the notes of my talk. So we conjecture it's fully faithful, but we have no idea how to prove it. So basically, if we knew how to prove it, we would module technical stuff will be done with Langlands. But so far, it's only GLN. Not good enough for you? Come on, this is usual. What do you mean? Yeah, okay. Sorry, I was joking. Yeah, so what's your name? What? Okay. So, indeed, in here you can take a very particular object, namely this skyscraper at a point. And then you can see what it will go over to this side. It'll go to some particular guy. And it'll be the Hecke eigensheaf. So the usual geometric Langlands à la Lemon is a particular case of this when you apply it to very particular objects, namely to skyscrapers. So the whole idea of this was to glue, to make it categorical, not to consider skyscrapers separately, but to make it as families over quasi-co. So that was the idea.
So we know that when you take a skyscraper sheet to the there, you get...
Well, if you believe in this, then if you take a skyscraper here, you end up here, and you're asking, why is it Hecke eigensheaf, right? So this will, thank you for the question. That's exactly what will be explained in my talk on day 3. So it's the Hecke property of Langlands correspondence.
This is how built into this diagram, right?
In fact, it is. So because these guys are fully faithful at the end of the day, and because this local equivalence is compatible with Hecke, it forces that if essential images coincide, this lower equivalence is also compatible with Hecke.
And it's an equivalence
Equivalence
of?
of?
It's the equivalence between the... between irreducible local system, G-check irreducible local system, and Hecke eigensheaf on G? Or you...
No, so okay, so you have to be very careful. So you can... So when you say the word irreducible local system, you cannot use the word equivalence because irreducible local system is just one guy. So what you can say is this. You can consider fixed irreducible local system and consider the category of eigensheaves for this local system. And if you believe in this equivalence, it will follow that this category is equivalent to vect.
For any group?
If you believe in this equivalence, for any group, it follows that the category of Hecke eigensheaves for irreducible local system is equivalent to vect, so that any eigensheaf is obtained from one standard one by multiplication by tensor product with the vector space.
What do you mean by irreducible?
One that doesn't admit reductions to any parabolic.
Does this force the eigensheaf to be perverse?
Good question. I don't know. It's exactly the spirit of Sasha in Ivan's question. I would guess yes. I don't know.
How about if your local system is not irreducible?
You get into deep trouble because of the difference between int-co and quasi-co. Because like if quasi-co, you basically have one point, you know what category. Well, you take the skyscraper, and that's basically what you have to do. If you have a singularity there, because of the difference of int-co and quasi-co, kind of even locally here, you have a much richer structure. So you actually don't know what to do in the non-reducible case. Take that trivial local system here, which is kind of as bad as it can be, and you'll get this full mess on the right-hand side. So we don't understand so well what this correspondence does on the neighborhood of the trivial local system.
So the irreducible local systems are some kind of smooth locus systems?
They are, so the smooth locus I think is bigger, but they are inside the smooth locus.
So it doesn't imply that at least the Hecke eigensheafs which correspond to irreducible local systems, that they're maybe you don't know that they're laying the abelian category, but are they finite in some sense? For example, do you know that they're finite?
Cohomologically finite?
Yes.
I don't know that. Maybe for GLN, maybe it's possible to prove it for GLN.
For GLN, I can imagine.
Yeah.
You have like a alternative construction.
So see, other than GLN, I don't know.
For GLN, I definitely know this for irreducible local systems.
Yes. Yeah.
You know this.
Maybe. So I don't know for the groups.
So it doesn't follow formally from smooth.
No. So I know very little about the T structure.
No, but cohomological finiteness is a different question. You started with a compact object on one side.
That's true. Yes. Sorry, Sasha. Yes, I know cohomological boundedness. He's right.
That's more or less what I want.
Yeah, that's right. Yeah, it's cohomologically bounded.
I think it should be easy to say that it's actually homological.
Perhaps. Yeah, I just haven't studied these questions. All right. So let's be done with this talk.